So this is the second part of our atomic history discussion. To review where we came from previously, we went from Dalton to Thomson to Rutherford. And Rutherford's model of the atom had positive protons in the nucleus. Chadwick added the neutrons in 1932. But we have protons and neutrons in the nucleus, and Rutherford said that the electrons were orbiting around the nucleus. Niels Bohr in 1913 gave those electrons specific locations. Bohr observed electromagnetic radiation coming from atoms, and he proposed that that radiation was a result of the electrons moving between specific energy levels. So Bohr proposed that electrons live in those specific energy levels, and there are 7 in each atom, 1 being the closest to the nucleus, and then they're nested with level 7 being the farthest one away. And electrons have the ability to move up and down between the energy levels. So if they absorb energy, they move up in energy levels. If they release energy, they're moving down in energy levels. This model of the atom is called the Bohr model of the atom. It looks kind of like an onion. So our nucleus is in the middle, and then all of the different energy levels add layers on the outside. So here's kind of a model of Bohr's atom. So when energy is absorbed, the electrons are excited and they move up, and then when they drop down, they release energy. And the color of energy depends on the color of light depends on how much energy is being released. And we're going to look at light a little bit later, because they can move up and down kind of stair-step-like, or they can move all the way up and then all the way back down. The important part is, where can we find these energy levels on the periodic table? Well, the energy levels correspond to the periods. So if you notice on the right-hand side, or on the far left-hand side, each row is numbered 1 through 7. So the row on the periodic table is also called the period. So it starts with 1 at the top, and then 2, and then 3, 4, 5, 6, and 7. Now, when we get to the middle part where the transition metals are, that doesn't restart at 1, and it's not 4 either. It starts at level 3, and it goes from level 3 to 4 to 5 to 6. When we get down to the lanthanides and the actinides, those don't restart at 1 either, nor do they follow 6 or 5. They are levels 4 and 5. We're going to ignore the letters for right now. We will come back to those later. Bohr's model of the atom really only worked for hydrogen. If he looked at the emission spectrum from sodium, so what light sodium gives off, he noticed 1 line. This made sense. It went from a high energy level to a low energy level. As we got better technology, we could get more detailed emission spectra, and Bohr observed that it was really 2 lines. So there was something going on with that higher level of energy. He proposed that each energy level actually has sublevels. So the first energy level has only 1 sublevel, the second energy level has 2 sublevels, the third energy level has 3, and the fourth has 4, and so on and so forth. The sublevels are noted by the letters S, P, D, and F. So the first sublevel is S, the second is P, the third is D, and the fourth is F. So what are sublevels? Erwin Schrodinger in 1926 developed equations that could show where these electrons were. And he was really, really good at math. We're not going to try to understand the math now. If you continue on in chemistry, you'll study it someday. But for right now, we're just going to look at the result of his math. And the results were that Schrodinger proposed that the electrons don't just behave as particles. A lot of times they behave as waves. So this is the wave-particle duality you may have heard of. And electrons, sometimes we have experiments that show that they act as particles, and we have other experiments that show that they act as waves. Schrodinger also said that the electrons don't live in specific energy level orbits, but they really live in clouds of probability, and those are regions where an electron of that particular energy will most likely exist. This is our most current model of the atom, and it's called the quantum mechanical model. So in the center of our atom, we still have our nucleus, still made up of the protons and neutrons. The only thing that's changing now is where the electron is located. Bohr said that it was in specific energy levels. Schrodinger modified that to say that the energy levels corresponded to probable locations that he called clouds. And these electron clouds have different shapes. So depending on the sublevel, changes the shape of the cloud where the electron might be. On the far left, you'll see the shape for the S sublevel. It's a sphere. As you increase energy levels for the S sublevel, the size of your sphere gets bigger. For the P sublevel, you see that they look kind of like dumbbells. You can put them all on top of each other and they turn into this flowery looking thing. We'll look at pictures of that later. And then for the D sublevels, we see lots of different options. And those start to get more and more complicated. We just need to know right now that they have shapes. That's what those sublevels mean. So we can see both the energy levels and the sublevels on the periodic table. So this is where those letters come back. And we divide our periodic table up into chunks. On the far left side, the alkali metals and the alkaline earth metals make up the S block. So 1s, 2s, 3s, 4s, 5s, 6s, 7s, so on and so forth. The transition metals in the middle make up the D block. So that has the D sublevel. So remember, those start at energy level 3. So we have 3D, 4D, 5D, and 6D. The far right-hand side of the periodic table, where we have our metalloids, nonmetals, noble gases, kind of the random scattershot of types of elements, we have the P block. So we have 2P, 3P, 4P, 5P, and 6P. And the very bottom, with the lanthanides and the actinides, that's the F block. So we have 4F and 5F. So we can combine our energy levels and our sublevels and determine where our electrons are most likely to be in our elements. And so how do we know where they actually go? We use our periodic table to write what are called electron configurations for each element. And they're unique for each element. We'll start to see patterns because there will be similarities based on where they're located on the periodic table. But we have specific ways that we can place those electrons in an organization, in a configuration for each element. And those follow a specific set of rules that we are going to look at next.